In this video, we continue looking at the chemistry of enolates. Remember that enolates are what result from the deprotonation of the alpha position relative to an aldehyde ketone or ester group. So in this particular video, focusing on the Michael addition reaction, what the Michael addition reaction is, by definition, is it is going to be the reaction of an enolate that we will form by treating an aldehyde or ketone with a base, and that enolate will react with a molecule that has conjugation. Specifically, generally that conjugated system that the enolate is reacting with will generally be the pattern of a carbon-carbon double bond conjugated with a carbonyl group. And then we can plug in our R groups as we like here for illustrative purposes. So we're going to be looking at what happens when we react an enolate, that was our deprotonated alpha position of an aldehyde or ketone, with a conjugated system. So let's go ahead and take a closer look at this reaction by going through an example where we will start in this Michael addition example by walking through the reaction mechanism for this particular reaction. So we are going to react here with the molecule that we would refer to as 4-oxo-2-pentanone. So we're going to go ahead and draw that 4-oxo-2-pentanone. So here's my 2 at position 2. We have our carbonyl group of the ketone, and then also at position number 4, we refer to that as an oxo group because there's another carbonyl group there. And pentanone should have 5 carbons in total. So this is going to be our 4-oxo-2-pentanone. Or depending upon what IUPAC version you're looking at, you could also refer to this as 4-oxo-pentan-2-one. So in this reaction, what we will do is we are going to react our starting molecule, our aldehyde or ketone, with a conjugated system. So I'm going to react with that conjugated molecule where we have our alkene conjugated to a carbonyl. So the general paradigm here is that we are reacting an aldehyde or ketone with a conjugated alkene ketone group, or aldehyde group for that matter. Now what's going to happen here is we will treat this with a base, which I'm going to refer to just as NaOR, where here the R could be an alkyl group. It could also be a hydrogen atom there. And so what's going to happen in this reaction in the first step is that since we have a base reacting with a molecule that has sp3 alpha proton or protons, we are going to use that base to remove a proton from that position. This is completely in alignment with the Claisen condensations and the aldol reactions that we looked at in earlier videos. So step number 1 of this reaction mechanism is going to be deprotonate at the alpha proton. And in this, the alpha proton is going to be what I'm labeling in red there in our diketone molecule. We also would have an alpha position over here in our conjugated molecule, but this is not an sp3 carbon and is not going to be as subject to losing its proton there. Same thing with this alpha proton over here. Even though this is sp3 and therefore it could lose its proton, it's not going to be as acidic as the proton right here, because when we lose a proton from our diketone here at the alpha position, we end up with a carb anion that's stabilized by resonance with both of the carbonyl groups to give 3 total resonance structures to stabilize it, whereas over here, there would only be 2 total resonance structures to stabilize the carb anion that you could create over here. And so therefore, when we bring in a base, the most acidic alpha position is the one right here. And so that is what the base is going to attack. It's more acidic than any of the other alpha positions. And there's actually a couple more that I didn't even mention here, which would be the alpha positions here and here. So lots and lots of alpha positions across these two reactants. We choose the one that is most acidic, the one that if we deprotonate will yield the most stable product of that deprotonation, in other words. Let's go ahead and show that deprotonation happening at this preferred location. So we go ahead and I'm going to show the two hydrogen atoms here, the two alpha hydrogens, explicitly. We will go ahead and react with our base, which I'm going to continue to abbreviate as just OR. Negative formal charge on that because it's bonded to the sodium, indicating to us that that oxygen must be an oxygen anion. Making it quite basic, it's going to come over, grab a proton from that alpha position acid, forcing the hydrogen carbon bond here to break and the electrons to go onto the carbon to create our resonance stabilized carbanion enolate intermediate. So going ahead and creating that, we are going to have still one hydrogen directly bonded here and our lone pair of electrons and negative charge there. Our other product of this reaction would be HOR, corresponding to the fact that we deprotonated there and that proton that we removed had to go somewhere. So now we have created, much like was the case in our earlier reactions, we have created a capable nucleophile here by deprotonating. It's quite nucleophilic, and so what it's going to do is it is going to come in and attack an electrophilic carbon of our conjugated molecule. So that's what I'll show here in step number 2. In step number 2, I bring in the product of step 1 there, which was our enolate intermediate, which would be stabilized by resonance. I didn't show all 3 of the possible resonance structures there, but you could if you wanted to. So we have our nucleophilic intermediate, and we're going to react with our conjugated molecule here. Reacting with our conjugated molecule, here's a plot twist from the earlier Claisen and aldol reactions. For in the earlier Claisen and aldol reactions, what we did was we took the carb anion that we created and we had it react with the carbonyl group of the other molecule that we were reacting with. In this case, though, what happens in these Michael addition reactions is that the lone pair of electrons actually attacks the terminal end here of the alkene group. And that is going to force the pi bond to come over to here to make a carbon-carbon double bond, and the pi bond between the carbon and oxygen to go up onto the oxygen. So in step 2, what I'll emphasize here is that the alpha carb anion nucleophile is going to attack the carbon-carbon double bond, not the carbonyl. We will get into, once we've gone through this complete mechanism, we'll go back and take a look in more detail about why it's the case that the lone pair of electrons here prefers to attack here to give way to the final major product rather than attacking that carbonyl group. So for now, we'll get through the mechanism and then we'll go back and kind of look at more of the rhyme and reason of why this step 2 happens the way it does in the case of conjugated molecules. So I have redrawn the portion of our starting material for this step that I drew in yellow. I'll highlight in yellow here on the product side. The new covalent bond comes off of this alpha position right here, so I'm showing that in red to illustrate that we've linked this carbon on our reactant side, that alpha carbon, the carb anion, with this carbon at the end of the alkene group. So I'm going to go ahead and draw that out. I'm going to draw it in blue for emphasis here. So we have our carbon-carbon bond there. Then we have our carbon-carbon double bond, methyl group at the very end, and we'd have an oxygen anion here. And so highlighting through this to illustrate who's who and what's what, we had our carbon-carbon bond here that was a double bond, now is a single bond on the product side. I've got both of those highlighted in green now, green and green. And continuing onward down the chain, we have a carbon-carbon bond that led to the carbonyl. Now it's a carbon-carbon double bond because we took the electrons to the pi bond and move those over to make this double bond. And then finally, what was the carbonyl group is now the carbon-oxygen single bond, and that bond to the methyl is still a bond to the methyl. And now, at this point, we are very close to the finish line of this particular molecule, because what we can do is we can now protonate this oxygen atom, which we will do. I'm going to go ahead and zoom out just a little bit here so that we have a bit more room to work. And I'm going to redraw that product of step 2 as we move onward into step 3 here. So in step 3, just redrawing the product of step 2, I'll draw that new carbon-carbon bond that we made in red, illustrating to us how this is another useful way to make carbon-carbon bonds to build complicated molecules out of simple ones. Our starting structure had an oxygen anion, and very much in agreement with the other reactions that we've learned about in this chapter, that oxygen anion that we create is ultimately protonated, and that's going to be step 3 here is protonation to create an alcohol group there. And to complete that protonation step, what we can do is bring in a base, which we have here as a result of step 1. We generated HOR, which could be alcohol or water. Regardless, it is going to be able to act as a proton donor. And so I'm going to fill that in as HOR. We will have the lone pair electrons from the oxygen come over, grab that proton from the acid. That forces the hydrogen-oxygen bond to break. And let's go ahead and draw out what results from that. Drawing everything in, color coding the same way that we did before. Double bond there. Oxygen is now an OH group. So I'll fill that in like so. And now at this point you might be saying to yourself, okay, I think I'm done because I've reached a final product where there's no formal charges on any of the atoms. But in this particular product, and products of these molecular addition reactions in general, what we've created here, the group that I'm highlighting in yellow, is what we refer to as an enol. That was a carbon-carbon double bond with an alcohol group directly bonded to it. What do we know about enols? Well, if we think way back, we recall that enols are subject to that process called keto-enol tautomerization. I know that's a rather gigantic word, and what it means is that it's a process of creating a constitutional isomer where the only atom that has moved is one atom in the entire molecule. Those are referred to as tautomers, molecules that are related as isomers where only one atom has moved. Bonds can move as well to move around carbon-carbon double bonds or carbon-oxygen double bonds. When we look from the perspective of the atoms, only one atom has moved. And so that's going to be our last step of this mechanism here is keto-enol tautomerization. So step 4 here, keto-enol tautomerization. And I'm showing the equilibrium arrow much toward the side of the product here because in this process, generally the enol form that we start with is predominantly converted into the keto form at equilibrium. So let's go ahead and show that keto-enol tautomerization process taking place. So I'm just redrawing the product that resulted from the step before, drawing everything out. And it's specifically going to be the enol group here that's going to react. I'm going to draw the bond to the hydrogen here of OH explicitly. And what's going to happen in this keto-enol tautomerization process is the same mechanism that we learned for keto-enol tautomerization before, which is that in this case we have base present. We had our OR ion, and the OR ion is going to come in, and what it will do is if we go ahead, the general base catalyzed tautomerization process is that we take the lone pair electrons from the base, they grab the proton from the hydroxy group as the electrons from that oxygen-hydrogen bond are used to come down and make a carbon-oxygen double bond, and simultaneous to that we would have another unit of acid available, something that's able to act as a weak acid, that is, such as alcohol or water, as we would have in our reaction mixture. And the pi bond between the two carbon atoms comes down and grabs that proton, forcing the hydrogen-oxygen bond to break and resulting in the following so-called keto tautomer. So we'll go ahead and write this out. So effectively what happens in this process is that what was the enol group becomes a keto group. So I've highlighted the corresponding parts of the starting material and the product that go along with one another, and that keto-enol tautomerization occurs because we have deprotonation of this OH group, and the electrons from that oxygen-hydrogen bond come down to make a carbonyl group. As the double bond comes over, it grabs a proton from our alcohol acting as the acid, and that's going to result in our product that we see here, where we have our final keto product. So when you're doing these reactions, when you're doing a Michael addition, you do need to take it all the way to the final expected product, because the enol will not persist in solution for very long at all. It will rapidly tautomerize to the keto form, such that you would not generally be able to even isolate the enol form of this due to that rapid tautomerization process to give this more favorable keto product. So now that we have got that out of the way, and we have predicted our final major organic product of this particular reaction, what we can do is start to take a closer look at what is going on in the second step of the reaction mechanism. If we go back here to where I've highlighted with my laser pointer in step 2, what we saw was that the nucleophile right here comes in and attacks at the terminal of the alkene group rather than attacking the carbonyl group. And this is very different from the Claisen reaction and the aldol reaction we learned, where when we deprotonated the alpha position, that deprotonated nucleophile came in and attacked the carbonyl. So why is the attack here in the Michael addition of this conjugated system different? Why does it attack over here and not at the carbonyl group? So in answering this question of why does the nucleophile attack the carbon-carbon double bond rather than the carbonyl at step 2, we need to take a look at the properties of the molecules that would result from each of those two scenarios. So the molecule that we see down here at the bottom, that was what resulted from the actual mechanism, which was the attack on the carbon-carbon double bond. So when we attacked the carbon-carbon double bond, that was right here at step 2, the carb anion came in, attacked that terminal of the carbon-carbon double bond, and ultimately led to the product that we see here. If, on the other hand, the attack had occurred at the carbonyl instead, the product that we would have got out of that reaction would have corresponded to what I'm going to show you here, which is where we would have linked the starting structure, that is this group that we deprotonated, we would have linked that, which I'll highlight in yellow on this product side as well for emphasis and to highlight who's coming from where. So if the attack had occurred at the carbonyl, what we would have done was deprotonated the same as we did in step 1. Then here at step 2, when our yellow dicarbonyl intermediate that is deprotonated there at the alpha position came over to attack, it would have attacked at this carbonyl instead of at the alkene group. And so what would have resulted is that you would have had a bond between that alpha position and what was originally the carbonyl. And that group that was originally the carbonyl would have become ultimately an OH group. And we would have had as well there the methyl group directly bonded and the 2-carbon chain there as well. And I'm going to highlight that for emphasis here in green to illustrate that these parts and pieces of the molecule go along with what corresponded to our conjugated molecule. So if the alpha position here had come over and had, rather than attacking the alkene group, it had come over and attacked the carbonyl group right here, that would have created the new carbon-carbon bond in red here in the upper right corner. And that carbon would have been connected to the OH group eventually, to the methyl group, and then to the 2-carbon chain with the alkene group in it. So this would have been our alternative product. So this is the product that is not observed. And it's kind of curious as to why it's not observed, because, we know that the carbonyl group here is electrophilic. So why isn't that the site where the attack occurs? Well, as it turns out, it goes back to the concept of thermodynamic versus kinetic control for reactions that are reversible. If we take a look at the properties of the two possible products, the one that is actually observed down here in the bottom circled in green, versus the one that is not actually observed that is in the upper right-hand corner, what we would find in comparing those structures is that the one in the upper right is the one that forms faster. Well, that sounds promising, but is less stable. The product has higher energy. On the other hand, the product on the lower panel is slower to form, but it is much more stable. And due to that greater stability, that is what's going to lead to this being the major product. If we look at an energy plot for the formation of these different possible products, I'll zoom out a little bit to show that, keeping in mind that the reaction is reversible, meaning it goes both in the forward and reverse directions. What happens is if we build an energy plot of the reaction coordinate or the reaction progress and the energy on the y-axis, the pathway leading to each of those two products, if we look at the keto product, which I'll put this red box around, it'll correspond to the red plot that I am going to show you here. That is the plot that has a slower formation, which indicates a higher activation energy barrier to climb over. So we'll make a nice tall activation energy barrier, but then it is more stable ultimately, which means that the final product has very low energy. And so if we continue that energy curve, we get through the giant activation energy, which is going to make the reaction happen slowly. Then if we get past that, it comes down to a very low energy. And that is the path that would lead to the so-called keto product here, the one at the bottom that I'm highlighting and outlining in pink. And we draw that energy curve with a quite high activation energy, the highest point of the curve here, and then low final energy to illustrate that this is going to form slowly because it's got a giant energy barrier to climb. But if it climbs that barrier, it's going to have a product that's very stable. On the other hand, with a blue outline, I'm going to draw the path that leads to the other possible product here, the product that forms faster. And we say the product forms faster. What that implies is that of the two possible pathways, this has the lower activation energy EA. So it has a lower energy barrier to climb over. And so I'm going to draw that. They would both start at this, both paths would start at the same energy because they both start from the same reactants. When we come to here, the activation energy for this reaction, the reaction following the blue path, the react that leads to the product up top, it's going to form faster, which means the activation energy is smallish. On the other hand, though, it's less stable than the product that is shown in pink. So the pathway shown in blue then needs to have a higher final energy than the pathway that was shown in pink, indicating that the final product is less stable. So when the final product is less stable, what that means is that the final energy of the product is higher. And keep in mind that I am not showing the entire reaction coordinate here. I'm showing an abbreviated reaction coordinate to illustrate the overall process here. In actuality, each of these individual steps of the mechanism would have its own activation energy. But what we're focusing on here is the activation energy of the rate limiting step and then abbreviating onward to the final product energy. So what happens here is going back to that fact that the reaction is reversible, what will happen is that the reaction can go forward, it can also go in reverse. And so keeping that in mind, what will happen here is that in particular, when the reaction is following the blue pathway leading to the higher energy final product, that pathway is going to very easily reverse because reversing doesn't require very much energy to get back over this hurdle and to get back to the starting structure. And there's not much energy difference between the starting material and the final product. So things circulate back and forth. And occasionally what will happen is that once the reaction has reversed, every so often a molecule will have ample energy to climb over the activation energy curve to take that higher energy intermediate pathway, like so. And once a molecule climbs over that barrier and makes it to the bottom of this curve, at this point, the energy is so low that the molecule becomes trapped there. It can't, at that point, reverse. So it becomes trapped as that particular product, the lower energy final product. And that lower energy final product, as it turns out, when we look at the lower energy final product, in other words, the more stable final product, that is this keto product that we have right here. And so that is our explanation of why it is the case that this Michael addition seems kind of weird at first in that the nucleophilic alpha position is attacking at the carbon double bond rather than the carbonyl. But what it comes down to is in this particular type of reaction of a conjugated molecule with an aldehyde or ketone is that we follow the energetics, and since the reaction is irreversible, ultimately it's going to favor the lowest energy pathway because this pathway at the very end gives such a stable product that once molecules reach that destination, they can't turn around and go back because the energy required to go back is just too insurmountable. They are too low energy at this point to turn around and reverse backwards. So the products following that pathway that leads to the lower energy product end up trapped because they are low energy at that point, and it would be a really high climbed curve to go back the other way. And so we describe that reaction as being under thermodynamic control. Thermodynamic control means that the product that is more stable is the favored product. So thermodynamic control is going to be the name of the game here, and I'm going to make sure I get this spelled correctly here for us. Thermodynamic control is the way that this system is going to work. Thermodynamic control refers to the situation where the products of the reaction are determined by the stabilities of the products. And since here, the driver of the reaction is that this product, the keto product, is much more stable than the other possibility, that indicates that this reaction is under thermodynamic control. It's ultimately the product that is most stable that is going to drive the outcome of the product, not the product that forms fastest, since the product that forms fastest can reverse back and forth, with every so often a molecule jumping over that energy curve and then getting trapped down here until eventually all of the molecules are trapped in this low energy state, meaning the final outcome is under thermodynamic control.